digital communication system. In the last lecture we have discussed block diagram of a digital communication system. So, if this is a source, so let us first discuss the transmitted part. So, these three are the main blocks, right, in the context of communication theory. So, if I just name these three, you are asked to map it. So, the exercise is that you have to rightly match. So, one should be mapped with, this is a source,
Be mapped with B.
very good. So, the first block 1 would be a source encoder block, which would try to represent your source with minimum number of bits, right. So, what is the task of source encoder? To efficiently represent the source, and since we are discussing binary, so in bits, right. So, this is the job of source encoder. So, efficiently represent it in form of bits in general, or yeah, for binary case it is bits. And the second block diagram is, yes. So, after the source encoder, we pass the bit stream to channel encoder, and what does channel encoder do? It introduces few bits or the redundant bits intelligently, right, systematically or intelligently, which can be further exploited at the, which we can further exploit at the receiver. For example, what is the one example which we have discussed? Repetition codes, right. And the third is C. So, once we are having bit streams, we have to convert it to some form of some waveform in order to transmit it over the channel. So, this is the channel. This channel can be anything, either optical fiber or the, so this is our channel, or the wire. So, accordingly, whatever waveform this channel supports, you have to map your bits accordingly to that waveform, right. So, let us try to first try to understand the third block, right, which is bit to waveform mapper. So, what we have discussed it in the last class, that we can do various mappings, right. So, if you remember, I would just go to the slide which we have discussed in the last class. Right. So, this is the binary scheme, or I would say 2 bit, we take 1 bit at a time, and there are 2 possible waveforms. In another case, we took 2 bit at a time, so there were 4 possible waveforms. So, similarly, you can take m bits, so there will be 2 to the power m various waveforms, right. So, anyone can take some number of bits and it can map it to some waveform which we represent by P1, P2, P3 and P4. So, we are trying to see or analyze the third block, which is bit to waveform mapper, how this mapping take place and how you can analyze this. Of course, what would be the time for each waveform? 2 TB, or you can write it as we are transmitting each waveform P1T, P2T, P3T depending upon the input bits. This is a bit to waveform mapper and this is the mapping table, right? You can call it mapping table. So, if the input is 0 0, you will transmit P1T, if input is 0 1, you will transmit P2T for capital T time, and of course, since you are taking 2 bits, you can write T as 2 TB. I hope up to this point the things are clear. So, what you are going to do at the transmitter? The question is what you are going to do at the transmitter. So, would you make a setup like this, that these are the 2 possible bits in input ports, and accordingly according to this input combination, one of the piece come out, right? This is just a conceptual diagram. Then what you are going to do at the receiver? So, one of these possible waveform will travel through the channel and will reach to the receiver through the channel, right? Now, your aim is to find out P1T, P2T, P2T, P what waveform was transmitted, right? Yes or no?
Yes.
So, for that I told you once that we will implement match filter. In the last class only I told you, but we have not derived it. So, just write that we will make matched filters. Match filter means filter matched with the all possible waveforms. So, how many possible waveforms are there? 4 waveforms. So, at the receiver what you can do, you can make 4 filters and each of them is matched to the corresponding waveform. So, H1T क्या है? H1T is the impulse response of first filter. Similarly, H2T is the impulse response of the second filter. So, this is a filter bank, right? You have to put a bank of filters and H1T, H2T, H3T, H4 will be, this will be matched with or matched to P1T and this will be matched to P2T. Match means HT must be equal to P of T minus T. So, if you want to make a match filter which is matched to the pulse PT, what you have to do? You have to design the impulse response which follows this so the maths we will see later. So, you have to design 4 bank of filters. फिर क्या करोगे इसको? You will sample it at capital T, sample it at capital T. So, here you are going to get any one of the PT, right. It can be either P1T or P2T or P3T or P4T, right, depending upon the input bits.
Yes.
For now we are saying there is no noise, otherwise some noise will also be added in the channel, right. In the channel means in the receiver front end. So, for now just assume that the noise is not present and the channel is perfect. Still there is a, at the receiver end you want to know what is the PT, right. Okay, just assume that the noise is there, WT is there, no problem. So, what you are going to do first? You are going to create a bank of filters. H1T क्या होगा? What would be your H1T? P1 T minus T. H2T you will design as P2 T minus T. H33 will be this and H4 will be this. Then we will sample the output, correct?
Yes, sir.
So, here we will get some value. Yes or no? So, if A1 is the highest, what it meant? Since you are having a match filter H1T, so if P1 was transmitted, just think like that. If two people who are of similar attitude or similar way, so the output corresponding to that will be high, right. So, if PT was P1T, A1 will be the highest, understood. So, depending upon the value, so we will take decision whatever is max, yes, we are going to say that whether P1 was transmitted, P2 was transmitted, P3 was transmitted or P4 was transmitted, right.
Yes. P1 is the maximum output, then P1 was transmitted.
Yes, if A1 is maximum. If A2 is maximum means most probably P2 was transmitted, right. So, as you can see here, the number of bank of filters is proportional to the number of waveforms, right. So, if other person take 3 bit at a time, so there will be 8 combinations and 8 different waveforms. So, at the transmitter also you have to generate 8 different waveforms, and at the receiver also you have to have 8 different filter banks, right.
Yes.
Yes. So, yes. So, can we somehow minimize these operations, because this is exponential in bits, right. It is 2 to the power 3. So, number of filter banks is exponential in 2 is some power, right. So, it is exponential, we call it when something is in the some power. So, it is exponential, it is in power, right, means agar 2 से 3 में जाते हैं then it will be 4 to 8, and then if you go to 3 to the 4, 3 to 4, then it will be 16. So, there is exponential increase, right.
Yes, sir.
So, can we somehow do the same thing? I mean, we do not lose in terms of performance, but we can somehow reduce this complexity, right. Can we do that? It's a question, right. So can we reduce this? Can we simplify, or in other words, so we can make it more efficient in terms of complexity, or we can simplify, and we simplify. So the answer is yes, and so you would ask how what is the tool which you are going to use to do that, right. In order to do that, so the tool is Graham Smith procedure, right. Let me check the spelling. Graham So, idea behind this is, let us take our previous toy example. So, idea behind this is, if there exist two bases or less than, there are 4 waveforms, right. If these 4 waveforms we can represent by linear combination of these two. Linear combination means weighted combination. So, what I mean, that P1 T is A1 phi 1 T or P11 phi 1 T plus P21 phi 2 T. So, if such a simplification possible, or such basis, these are also called basis. We will see what is the meaning of basis. So, what I am saying, for example, phi 1 phi 2 exists such that you can write okay, P2 over 1, so P1 2, ठीक है. So, P12 phi 1 T plus P22 P3 T is equal to P13 phi 1 T plus P23 phi 2 T. So, P4 T is P14 phi 1 T plus P. So, this P11 P12 are the some scalar values. This P11 up to P4 P14, similarly P21 up to P24, all of these are some real value or some scalar value P4, sorry, It means if this is the case, what you can do at the transmitter, instead of having 4 different waveforms generator, what you can do? You can have 2 waveform generators, phi 1 t and phi 2 t. Just what you need to do? You need to provide a mapping table which maps 0 0 to 0 0 to किस में मैप करेगा? P11 P21, yes or no? Then P11 will go here and P21 will go here, right? Yes or no?
Yes.
So, what if we can do that, that we can have this mapping, that 0 0 is mapped to P11 P21, 0 1 is mapped to P12 P22. Similarly, P13 P23 P14 P. So, we just need this mapping or this encoding table, which you can put in the software also, right? And then this part will be multiplied with this, and this coordinate, you can call it coordinate or the coefficient, would be multiplied by this, multiplied with this. So, you can generate all the possible waveforms, yes or no? This mapping table with only 2 waveforms, right? Here we had 4 different waveforms depending upon this. So, rather than generating 4 waveforms, you have now fixed your phi 1 t and phi 2 t, and now just as per the input combination, input bit combination, you are generating these coefficients, correct?
Yes.
So, the similar thing you can do at the receiver. What is the aim at the receiver? Just you need these coefficients, right? So, what you are going to do? I told you earlier that you have to have a match filter, right? But this match filter will be now matched with phi 1 this match filter will be, second match filter will be matched with, or the impulse response of second will be phi 2 t minus t. ठीक है? So, at the receiver, whatever you receive, you will pass it through it, sample it, so what will you get? Now, just assume no noise case, no noise scenario. So, any of these 4 combination will come here. So, here you will get A phi 1 t plus B phi 2 t, right, where A can be either P11, where A can be P11, P12, P13 or P14, right. A can come from this and B can be anything, right, or you can say that A comma B can be any of these 4, right? Yes or no?
Yes.
So, here once you do this, you pass this signal through this, what happens here? You will extract A, you will extract B. My claim is that once you pass this type of signal through this, you will be able to extract A and B. And how this works, we will see it just in few seconds or few minutes. यहाँ तक समझ में आया? Earlier what we were doing, we were have to design 4 different match filters, and accordingly you have to take decisions. But here
Get the magnitude, right?
here
In form of A and B, that is magnitude of phi 1t. That will be A, correct?
see, your aim is, for example, there is no noise scenario, right? But still at the receiver you do not know whether it was transmitted, this was transmitted, this was transmitted, or this was transmitted, right? There are 4 possibilities.
Correct.
So, if you can somehow tell, so at the receiver the form will be A phi 1 t plus B phi 2 t, the form. So, your aim must be to extract A and B. Once you know A and B, you can provide a, since you have this decoder table here, you can simply decode it, right?
Correct.
So, now we have to see how this works, right? So, before that, what we are going to say, I told you that there exists a basis, right? We have assumed it, right? That our P1t, P23, P4t can be represented using 2 bases, right? But what is the property of this? So, first let us say property of set of basis, or you can say set of basis functions. So, in our case we have assumed that there exists phi 1 t, phi 2 t, which can represent all these 4 waveforms. So, what is the property which must be satisfied? The first property is that they are unit energy signal. क्या है? The energy of these phi 1 t, phi 2 t as unit and the second property is that phi 1 t into phi 2 t d2 is 0. It means ये कैपिटल T क्या है? कैपिटल T क्या है? टाइम ड्यूरेशन ऑफ दिस वेवफॉर्म्स. So, I assumed that P1t, P23, P4t can be represented using orthonormal basis phi 1t and phi 2t. We call it ortho. If these two satisfy orthonormal basis. Why this term orthonormal? Because they are orthogonal. This is the property of orthogonality. ऑर्थोगोनल क्या होता है? अगर this is called orthogonal, right? Vector v1, vector v2. So, if inner product between vector v1 and vector 2 is 0, we call it orthogonal. Yes or no? Yes or no? ये दोनों वेक्टर हैं. आर दे ऑर्थोगोनल? plot it I and j, or x 1 I and 1 j, this is one vector, this is this vector. What is 2 I minus 2 j? 2 times I and minus 2 times this. So, you will see they are ortho, and if you just multiply the term by term, 1 is to 2 is 2, 1 is to minus 2 is minus 2 is 0. So, this is called inner product or the dot product. Yes or no?
Okay.
So, similar thing happens here. The dot product of two vectors is 0. We call those vectors as orthogonal, but these are the vectors in 2D space, right, which we are very familiar with, but these are the waveforms. So, what is the inner product or the dot product between two waveforms? This is the definition. Yes, ठीक है.
Yes.
So, by this you can use to remember for the analogy, right. Two vectors are orthogonal when the inner product between them is 0, and two waveforms are orthogonal with inner product between them is 0, but inner product is defined for waveforms like this. ठीक है? Okay. So, we can call it orthogonal, and then since they are having unit energy, right. अभी देखो, if this is one vector 1 and 2, which or 1 and 1, what is the magnitude of this? Under root a square plus b square, which is root 2. So, this is not unit, right, but if we had a vector 1 by root 2 I plus 1 by root 2 j, which you can also write like this, what is the vector norm or the magnitude or the length of this vector? So, if you just draw this vector in 2D, 1 by root 2 here, 1 by root 2 here. So, this point, what is the length of this? 1 by root 2 square plus 1 by root 2 square under root, which is half 1, right. So, you can say that this vector is unit norm. क्या बोलोगे? Unit norm. Norm means for 2D vector case, norm is length. ठीक है? Anyway, so for waveform case, what happens? We calculate energy, and if it is unit equal to 1, we call it, क्या बोलेंगे? Unit norm. Therefore, or the normal vector, therefore we call it orthonormal. So, they are orthogonal as well as normalized, you can call it. They are normalized in their energy, or the, yes, normalized in the sense of their energy, therefore they are called orthonormal basis. अभी clear है? Abhishek? Okay, so if these two properties are satisfied by phi 1 t and phi 2 t, let us see what happens. You have passed a phi 1 t plus b phi 2 t, and you are convolving it with, in the first case, with phi 1 t minus t, and in the second case, or in the second branch, we are convolving it with this. So, our aim is it should be equal to A and it should be equal to B. We should be able to find out the weights corresponding to phi 1 t and phi 2 t. यस, यही एम है ना हमारा. सो इसको देखो, ए phi 1 t convolved with phi 1 t minus t plus b phi 2 t convolved with phi 1 t minus t. Right? Yes or no? अभिषेक, हम कन्वॉल्व ही तो कर रहे हैं ना, एंड कन्वॉल्यूशन इज ए लीनियर ऑपरेशन. सो यू कैन राइट दिस कन्वोल्यूशन विल, convolution of these two with this is same as convolution of this with this plus convolution of this with this. Yes or no? अभी इसको सॉल्व करो. क्या होता है कन्वोल्यूशन? phi 1 tau, if you remember we have studied convolution of xt with ht. क्या था वो? x tau h t minus tau d tau, right? Yes or no? बताओ. So you can write phi 1 t into phi 1. So you have to write t minus tau. Okay. So t minus t. One second. T minus tau. H t minus tau. One second. We can also do that. Hmm? Hmm? नहीं, आवाज, योर वॉइस इज नॉट क्लियर. योर वॉइस इज नॉट क्लियर. नाउ प्लीज ट्राई टू स्पीक अप. Still not clear. Your voice is not clear. Please type your question. It will be b pi 2 t. Okay, a phi 1 t. Okay, one second. Maybe I have done some typo. So this is what you have written, I think. क्या लिखा है अभिषेक सिद्धेश गुप्ता ए पाई 1। ओके, तो कॉमन नहीं लिया है, वो तो होगा ही ना। आई मीन दिस विथ यू आर सेइंग दिस,
Yes, yes.
सो कॉमन तो होगा ही ना, बिकॉज इफ यू रिमेंबर xt convolved with ht is, say अगर if you are having alpha xt convolved with ht तो क्या होगा बताओ? It is same as alpha because it's a constant, right? X tau ht minus tau d tau, which is same as alpha x tau ht minus tau d tau, which is same as alpha x convolved with h। ठीक है ना,
Yes.
वो सेम है, इट्स नॉट, ठीक है ना, चलो इट्स ओके। सो दिस इज द केस। नाउ we will prove it later. I would just write this, that this is same as a phi 1 t into phi 1 t dt zero to capital. So this convolution is same as this. The proof we will do later. So if this is the case, what is this first term? बताओ, if this is the case, just check the property of orthonormal basis, this and this. So by applying these two property here, you can clearly see that this will be 1 and this will be equal to 0. So the answer will be A. So what I am going to tell here, so this is same as, mathematically you can prove it, we will do it later, that first branch is same as and the second branch. So bank of match filter please ask me if you have any doubt. We have not proved it that once you pass this a phi t, a phi 1 t plus b phi 2 t type signal through the first branch, which is the first branch of this bank of match filters. I told you that this is same as, convolving these two is same as multiplying this with phi 1 t and then integrating it 0 to phi. This I am claiming, which the proof will be done later. You understood my point or not? So this is same thing, whatever I have drawn here, what I am saying, passing this and then convolving this quantity is same as this, you multiply this whole thing with phi 1 t, this thing, and then integrate it with 0 to t. So branch of each match filter will work as a branch or the correlator filter. Whatever is the input, what you are doing, you are taking inner product of this with phi 1 t, which is also called that you are trying to find out how much this signal is correlated with phi 1 t. So, this is also called correlator. You understood my point?
Okay.
So, rather than doing this operation, that passing this signal through a match filter, if you want to know how much this is matched with phi 1 or what is the weight of this with phi 1, you can do the same thing by doing the correlator filters, bank of correlator filters. So, these are mathematically same, either you do this or that we will do proof later. So, if this is true, then easily you can see whatever we pass through here, weighted summation of phi 1 and phi 2, we will get first factor here and the second factor here by using this. Yes or no? See here, this you do here, just take phi 1 inside plus b phi 1 inside, and using the property of the orthonormal basis that they have unit energy and they are orthogonal to each other, right. So, by using these two property, you can say that this is A, and similarly you can apply this to here. So, if we apply correlator filter, the second output of the second branch will be this, you multiply it with the phi 2 t dt 0 to t. This is same as what? Doing this, which we will do proof mathematically later. This is same as this. So, passing this through the match filter is same as evaluating this, the correlation of this with phi 2 t.
Got it.
So, simply you can now write it as a phi 1 t into phi 2 t dt plus b 0 to t phi 2 t into phi 2 t dt. So, by using the property of the orthonormal basis, this integration will be 1 and this integration will be 0, because they are orthogonal to each other and they are normal, means they are normalized with their energy by. So, the answer will be B. So, the output of the second branch will be B. So, once you have this A and B, you can easily find out what was transmitted. Yes or no?
Yes.
But of course, this is the case when no noise, है ना? Anyways, so earlier what we were doing, we were using, if we did not had this concept of Gram-Schmidt orthogonalization procedure, we had no choice but to transmit 4 waveforms and accordingly design 4 bank of match filters, right? Yes or no?
Yes.
This you can convert to correlator filter, that is the separate issue, but you have to have 4 branches. But now as you can see, both at the transmitter and at the receiver, you can reduce it to 2 branches, right? But under the assumption that these 4 waveforms can be represented by the orthonormal basis of dimension. So, these are called, this together are called basis and each are called basis function. So, basis is a set of all the orthonormal basis functions. Phi it is basis function which is used to represent the given set of waveforms. So, what does Gram-Schmidt orthogonalization procedure do? Just think it as a algorithm. If Gram-Schmidt orthogonalization procedure is a algorithm, at the input what you have to provide? This set of all 2 to the power m waveforms, yes or no, where m is number of input bits, and it will reduce it, or it will try to give you set of k possible orthonormal basis functions. So, each f1 t to phi k t constitute a set. This is called basis or orthonormal basis, orthonormal basis, where this k will be less than 2 to the power m, or at max. Sometimes if your waveforms are such that they are already orthogonal and already normal, then you cannot further reduce it. So, the k can be either equal to 2 to the power m or less. You understood my point? So, Gram-Schmidt procedure gives you minimum number of orthonormal bases which can be used to represent all the possible given waveforms. Yes, yes, that's you have. That's what I am saying. You should choose orthonormal, of course, but it gives you flexibility, right? As I said, no, it will not increase. See, first you have, see, we are going backwards now. Someone can come up, okay, this third, a very 8th grade person, 8th grade means a person who studies in 8th grade. You are told that just take sequence of bits, accordingly you need to send the waveforms, yes or no? So, he will pose this question to you as an engineer, that how will you now analyze the whole system or design the whole system, right? And can you some comment that these waveforms are good, these waveforms are bad? These type of questions will be posed on you, right, by some school kid. Sir, मैं तो 4 कोई भी waveform ले लूँगा. Now you tell me design problems as well as performance, how my waveforms will perform, yes or no? So, you will say, okay, give me any 4 waveforms, or so I will first try to design my system by using minimum number of filters or minimum number of circuitry, right, yes or no? So, this is a design aspect, right? Then there might be the performance aspect. For example, a person A comes up with 4 different waveforms, right, 4 different waveforms which can be represented using phi 1 t and phi 2 t, and the 4 points are such that like this. It can be, right, this can be your P1 t. कैसे लिखोगे P1 t को? अगर this is P11, this is P21. This is called geometrical representation of your waveforms, yes or no? P1 t is P11 phi 1 t plus P21 phi 2 t, yes or no? Similarly, you can do, my bad, similarly you can represent your P2t like this, P3 like this, and P4 3 like this. some other person can come up with 4 other waveforms which might have some other orthonormal basis. You can call it phi 1 dash t and phi 2 dash t, yes or no? And his points lies this. ठीक है. So of course, if you design this system or design this system, the complexity is same in terms of design aspect, right? Yes or no? At the transmitter end you have to have 2 orthonormal bases, and at the receiver you would have bank of correlators, right, with phi 1 dash t and phi 2 dash t for this case and phi 1 t and phi 2 to this case, right. Of course, then you can ask what is the power or what is the total average energy, right. By average energy I mean length of this, length of this, length of this, length of this. Then A and B said, sir, all are same. In one, I mean the length of this plus length of this plus length of this. So what is the average energy of this? First let us try to see average energy. Now we are moving towards the analytical aspects. Design aspects is clear, right. Synthesizing or synthesis part is clear that both are same. A and B, I mean the तुम्हारा क्वेश्चन का ही जवाब दे रहा हूँ मैं, सुनो तो पहले पूरा. फिर हाँ, फिर तुम क्या बोलोगे, डिज़ाइन मेरा पूरा हो गया, बट इफ़ आई ट्रांसमिट P1T, P2T, P3T, एवरेज एनर्जी मेरी कितनी कंज्यूम हो रही है, हाउ मच इज द एवरेज एनर्जी कंज्यूम्ड एट द ट्रांसमीटर, yes or no? This question you might ask. So I would give you formula. What is the average energy? The formula is, what is the probability that P1T will be transmitted? This is your bits 1 by 4, right. Just you say that there are no bias. So 0 0 probability of 0 0 0 1 1 0 1 1 is all equal, all are equiprobable. So 1 by 4 times the energy of P1T, whatever is the energy, 1 over 4 times energy of P2T, 1 by 4 times energy of P3T plus 1 by 4 times energy of P4T. Energy is what? This length. The formula of energy I have written this, right. इसमें स्क्वायर रूट होगा क्या? Let me think. See, here it does not matter because even you square it, it will be 1. But what is the definition of energy of a pulse? Let me see. If somebody knows, Gulshan, just put it. Just hang on with me, you will understand. Okay, the energy is this only, right. So what will be the energy? Under root of P1 square T dt, right. So the magnitude of this is root of energy of P1, root of energy of P2, root of the length, yes or no? चलो थोड़ा सा तुमने फिर डाइवर्ट कर दिया, बट ठीक है. देखो ये क्लियर है कि नहीं? व्हाट इज द एनर्जी ऑफ P1T, मुझे बताओ. दिस इज द डेफिनेशन, ठीक है। जस्ट पुट इट हियर, प्लीज ऑल ऑफ यू डू इट। यस और नो, ये क्लियर है? अभी ठीक है? सो व्हाट इज दिस P11 स्क्वायर 0 to t phi 1 square t dt, yes or no? Is it clear? So what would be the answer? ये क्या होगा? 1 by the definition of orthonormal basis, ये क्या होगा? 0. So this third term will be 0 and this is equal to P11 square plus P21 square. So as you can see this, ये value क्या है? This the length is under root P11 square plus P21 square. So this is under root of energy. Yes or no? If this is E1, this will be square root of E1, this. So if you have geometrical representation of your waveforms, you can check a lot of things. What is the energy of each waveform and what is the average energy? So average energy अब क्या हो जाएगी बताओ? 1/4 of E1 plus E2 plus E3 plus E4. For this case, B came up with 4 different waveforms. You can call it P1 prime t, which you can write as P11 prime, P21 prime or dash. Similarly, P2 dash t, P3 dash t, P4 dash t, and you can write the coefficient as P12, P22 dash dash prime prime. This is as P13, P23 dash dash. This is P14, P24 dash dash. Yes or no? So energy of this, average energy of this geometrical representation of this constellation would be 1/4 E1 dash plus E2 dash plus E3 dash plus E4 dash, right? So this is root of E1 dash, this length is root of E2 dash, this length of root E3 dash. Yes or no? So average energy of this constellation will be 1/4 E1 dash plus E2 dash plus E3 dash plus E4 dash. So you will say to A, the person who is transmitting less energy, for the transmitter point of view, I am a transmitter who is transmitting these 4 waveforms, right? Either, so for case of A I have designed one transmitter, for the case of B I have designed one other transmitter. So who the transmitter will say, जिसका ये average energy, whose average energy is less, I would say that is better. So what A and B did, they said okay, the energy is same, we are designing these constellation points in such a way that the average energy of both is same. Understood, Abhishek? So first number of filters or number of waveform generator for the case of A is phi 1 t and phi 2 t. Second, the average energy which you are using at the transmitter is E average. B के केस में number of waveform generator is 2, same phi 1 prime t and phi 2 prime t, and second average energy is E average prime, but both A and B has designed their constellation such a way that E average is equal to E average dash. ठीक, अभी ठीक है. So transmitter के point of view से, for the point of view of the transmitter, both are equally good, but at the receiver, now think at the, so this is the point of view of a receiver, point of view of a transmitter. Now let's think from the point of view of a receiver. A, you have to design two correlator filters, match filter or correlator filters, right? Number of branches 2 for correlator filter or match filter. Second, what is the error performance or immunity towards noise or the performance if there was no noise? तब point of, if the case is no noise, then receiver को कुछ problem होगा क्या? Whether you implement A's waveforms or B's waveforms, बोलो, नहीं होगा, राइट? क्योंकि रिसीवर को क्या करने का है, बस these two he will implement and whatever will come out he will tell accordingly, right? Whatever the weightage of phi 1 t and phi 2 t. So no problem, right? No noise case, both are equally good. Now comes the performance over noise. Yes or no? बोलो. कि you have this type of setup, so in case of A's design where your constellation point was something like this, but in the case of B the constellation points was like this, right? Yes or no? So मुझे अभिषेक ये बताओ, if there was no noise, xt was A phi 1 t plus B phi 2 t, right, where A and B will be decided on the basis of the stream 0001 1011. So at the output of this or at these two branches you will get this and this, yes or no? But if there was noise, what would happen? There will be some addition or there will be some deviation from these 2 points at the receiver end. So you have sent this, but you might get this, yes or no? So, your noise can be such that it will bring this, you have transmitted this white one, you have sampled it here, and your noise has taken this to the closer to the second point corresponding to P2T. So, you will say you will have some AB, yes or no. So, here you have A comma B, this is P11 P12, this is P11 P21, this point is P 12 and P22. So, if your A and B is closer to this, you will decide in favor of second waveforms, yes or no. But here if you can see, you have transmitted same P1T or P1 dash T, even though some noise will take it up and down, or in this vicinity you have transmitted this, but you have transmitted this many times, the noise will take it here and there, right, here and there. But every time, since your second constellation points or second points correspond, all other points corresponding to the other waveforms are quite away from this, yes or no. So, the performance intuitively will be better for B, yes or no. So, now you have a complete picture that you can now design your transmitter, you can design your receiver, and now you can also say which constellation is good, right, on the basis of distance or the intra distance of the points, right, yes or no. Intuitively, of course, mathematically we have to see that what is the bit error rate, etc., right, yes or no. So, I hope now your all the queries are resolved. हाँ, तो अब हम कुछ न्यूमेरिकल करेंगे, यहाँ तक क्लियर हो गया. So, let us do few numericals which I have designed for you people. चलो, हाँ, Abhishek, I can't hear you. Okay. So, till now we have said that this is a procedure which is called Gram-Schmidt procedure, which will give you the set of orthonormal basis functions, orthonormal basis functions, set of basis, Gram-Schmidt basis is set of orthonormal basis functions, yes or no. But what is that procedure, that algorithm I have not told you yet, right? Have we discussed that, Abhishek? Okay. So, let us first discuss how to evaluate the orthonormal, OAN means orthonormal basis functions, or the set of this orthonormal basis functions from the given set of waveforms. One thing you must notice that all the waveform must have finite energy, that we will see later. चलो ठीक है, अभी इसको छोड़ो, ठीक है, from the given set of waveform, yes or no. तो how to evaluate that? So आपके पास क्या है, you have input, what is the input to this algorithm, P1T, P2T up to P2 to the power mt. So let us call this 2 to the power ms. Generally ठीक है, उसको k लेते हैं जनरली नंबर ऑफ बिट्स को, बट ओके n ले लो इसको, सो लेट्स कॉल इट n, इट्स ओके. And the t will be from 0 to capital T, and this capital T is equal to mTB, right, because you are taking. So you just call it T for the sake for this generalization. Just there is some T and we have these n waveforms which you are using for time duration 0 to T. So procedure क्या है? Step 1, phi 1t will be equal to, बोलो, P1t divided by square root of energy of P1t. तो आप क्या बोल रहे हो? जो पहला वेव फॉर्म है मैं उसको नॉर्मलाइज कर दूंगा उसकी, आई विल और नॉर्मलाइज दैट विथ इट्स एनर्जी एंड आई विल कॉल इट एज phi 1t. ठीक है, इज इट क्लियर? वी आर डिस्कसिंग ग्राम स्मिथ, what was the spelling? Gram SCHMIDT, okay, so Gram Smith orthogonalization or orthonormalization process. Okay, just call it Gram Smith. So next, अभी क्या करोगे आप? टेक सेकेंड वेव फॉर्म P2T, सेकेंड इनपुट वेव फॉर्म, subtract it with the projection of P2T over phi 1t. Have you understood this second term? Let's call it in a new slide. Step 2. So what we are going to do here, this is your second waveform. First project it over phi 1t, subtract it with the P2T, just call it at phi 2 tilde, and phi 2t will be phi 2 tilde t divided by energy of phi 2 tilde t square root, just normalizing it with the its square root of its energy. ठीक है, क्लियर है ये चीज? Is this clear to you? Yes or no? Is this clear? Yeah. This term is, first you have to project your current waveform P2T over the previous orthonormal basis, over the previous orthonormal basis. So this is like how much this lies over phi 1t. Phi 1t क्या है? Whatever was the P1t, we have just normalized it. Yes or no? Next, what you are going to do, you have to first try to find out how much that P2t lies over the previous basis. So what is the rest? This will be the rest. Yes or no? So this rest will be orthogonal to the previous basis. So this is the rest. So once you have projected it over it, so this will give you quantity, how much is that over this, and then you have to multiply with phi 1t to have the direction, right? Yes or no? Okay. So, after this you will get phi the another phi 2 tilde t, and just you are normalize it with its energy, because you know that all the bases are always normalized. Okay. So, now you have phi 1 2 and phi 2 t with you. There is some p 3 t. So, what you have to do next? By following this similar approach, you have to first project your p 3 t over the previous basis. There are two previous bases, p 3 t, phi 2 t, and whatever is the remaining is actually orthogonal, but just you have to scale it or normalize it to make it orthonormal, make it normal. So, just you have to energy of phi 2 t. Yes or no? ठीक है. So, this is your space, orthogonal space, p 3 is somewhere here. So, you just project it over here and here. So, you will get a new vector and the rest will be orthogonal. So, this will become phi 3 t. So, this is just a geometrical way, but this is the procedure. Is it okay or not? And you have to repeat until you consume all the p's, all the waveforms. If you have any query, please ask. Till step 2 you had only one phi 1 t. So, you have to project your p t over phi 1 t. Now, you have two orthonormal, two bases with you. So, you have to first see ki whatever basis I have, what is the amount of that p 3 t for the given bases, for the basis I have, and the rest you have to design a new one, right. You understood my point? Yeah, it is something like that. So, this is how you are going to evaluate your, and you have to repeat it until all the p's up to p n you consume it, right. So, let us take an example to better understand this concept. If you want some 5 minutes, you can take it. Yeah, please go. No, you should be here, just stay calm and take 5 minutes break. In 5 minutes you can come. So, okay, so the part 2 will start after 5 minutes. ठीक है, चलो.